Hello everyone, I am back with part 2 of Electrostatics NSEP PYQ solutions. And in the last part 1 we covered till question 29. So today we'll be covering from question 30 to question 70. So last question that we covered was question 29, and it was this SHM related question, and question 30 is related to solid angle and flux. So let us see. Question 30 says a non-conducting spherical shell of radius r surrounds a point charge q. The electric flux through a cap of the shell of half angle theta is. Okay, so let us first understand what is half angle. What is solid angle? So let me draw a diagram. So assume that this is a cone and this is the surface of the cone. I am representing it with lines. All the lines are originating from this vertex, and let me draw some uh, surfaces which are parallel to this surface. The surface area of this is S1, this is S2, and the distance from the vertex is R1 and R2. So solid angle is defined as the (3D) angular region enclosed by lateral surface of cone and its vertex. And it is represented by the symbol ohm, which is also seen in electric current, where it represents resistance. So here this is solid angle is given by the surface area divided by the square of the distance which it is at from the vertex. So this will also be equal to S2 by R2 square. So let us now solve the question. So we need to find the flux through a cap of shell of half angle theta. So let me draw the half angle, let me draw the shell. So assume that this is the shell and this is the center. So this will be radius r, and we are taking an element at angle phi from this vertical line. So this angle would be d phi, and this will subtend a ring like element on this cap. Basically I am trying to find the area of this cap so that I can apply this formula and find the solid angle. So let me write the area of this. So area will be given as, since this is r, so this radius will be given as r sine theta. So area can be given as 2 pi r sine theta multiplied by r d theta, r d phi, sorry, this will be phi also, because this ring can be cut from the middle from somewhere here, and this can be converted into a rectangle, right? And we know that the circumference will become the length of this rectangle, which is 2 pi r sine theta. And since this length is given as r d phi, so this will become r d phi, right? So now this will be the area. So the total area will be from 0 to theta, right? Because if we vary this phi from 0 to theta, then we will cover the entire cap. So this will become 2 pi r square cos phi from theta to 0, because it will be minus cos, so I have exchanged the limits. So this will be 2 pi r square 1 minus cos theta, right? And solid angle is given as area by r square, so this will become 2 pi 1 minus cos theta. Okay, so now let us see some shapes. So if the half angle is equal to 90 degree, let us see what will happen. So if the half angle is 90 degree, then it will mean that the solid angle of hemisphere is two pi r square multiplied by 1 minus, sorry, r square got cancelled, right? 2 pi r 1 minus cos 90, which is 0. So this is 2 pi. Similarly, the solid angle for sphere will become double of this, which is 180. So for sphere it will be 2 pi 1 minus cos 180, which will give us 4 pi. So we know that the total flux through a sphere, total flux due to a point charge, is given as q by epsilon naught, and this covers the entire sphere. This point charge is surrounded by sphere. Hence, q by epsilon naught flux is distributed over 4 pi solid angle. So if we use unitary method and we need to calculate the flux through this solid angle 2 pi 1 minus cos theta, since that is what the question is asking, so by unitary method, flux through solid angle theta is given by q by epsilon naught multiplied by 4 pi multiplied by 2 pi 1 minus cos theta. So this will be given by q by 2 epsilon naught 1 minus cos theta, which is the answer. Hope this is clear. This was a 3-marker question from 2015. So answer will be option B. So now moving on to question 31, it says that a charge plus q is placed at a distance of d from point O. A conducting body surrounds point O such that q remains outside. The electric field at O due to induced charge is. Okay, so we need to find the electric field due to induced charge. So let me draw the situation. So imagine this is point O and q is placed at a distance of d, right? And conducting body surrounds point O such that q remains outside. So the electric field at O is equal to 0 since field inside conductor is 0. And also we know that electric field at O due to q is given by kq square divided by d square in the minus I direction. So electric field total is 0, which is the sum of electric field at O due to q plus electric field at O due to induced charges. So electric field at O due to induced charges will be equal to minus of electric field at O due to Q, which will become kq square d square I cap. So it will be option V, which is 1 by 4 pi epsilon naught q by d square directed towards the charge q. So moving on to question 32, we have an electron is injected directly towards the center of a large metal plate having a uniform surface charge density of -2 multiplied by 10 raised to power -6 coulomb per meter square. The initial kinetic energy of electron is this much. The electron is observed to stop just as it reaches the plate. Therefore, the distance between the plate and the point from where the electron was injected is. First, let us draw the situation. This is a plate, and they have calculated the answer by considering it to be a conducting plate. This has some charge density and it is negatively charged, and an electron is injected from some distance d, and it has some kinetic energy initial. So let us first calculate the electric field due to this plate, which is given by sigma by epsilon naught, and sigma is -2 multiplied by 10 raised to power -6 divided by 8.85 multiplied by 10 raised to power -12 Newton per coulomb. So we know that due to energy conservation, initial kinetic energy is equal to work done by electric field plus final kinetic energy. So this is 0. So initial kinetic energy is 1.6 multiplied by 10 raised to power -17 joules is equal to E into E multiplied by D, where E is small e and the second E is this electric field. So this will be so when we calculate D, it comes out as 4.4 multiplied by 10 raised to power -4 meter. So option A is correct. Okay, so moving on to question 33, we have a charge Q is situated at the origin. Let EA, EB and EC be the electric fields at 3 points ABC. Therefore, so we have to calculate the fields at ABC. So let me draw. If this is the x-axis and this is the y-axis, so z-axis will be in this direction, and the charge is situated at the origin. We need to find the fields at A, B and C. So at A is somewhere here, B is somewhere here at -1, -2 and 4, and C is somewhere here at 2, -4, 1. So the field at A can be written as since we don't know this R, I will write this in the vector form, which can be written as kq by r square multiplied by r vector divided by magnitude. So this will become kq by 2 square plus 3 square plus 1 raised to power 3 multiplied by 2i minus 3j minus Z. So similarly, EB can be written as KQ by root of 1 square plus 2 square plus 4 square multiplied by minus I cap minus 2j cap plus 4k cap. And similarly, EC can be written as KQ by 2 square, so this will be raised to power cube plus 4 square plus 1 raised to power cube multiplied by 2i cap minus 4j cap plus k cap. So now let us see the options. EA is perpendicular to EB. Let us check. So if EA is perpendicular to EB, it will imply that EA dot EB is 0 because cos 90 will be 0. So let us check if this is true. So we have KQ is common. So this will become, this is 4 plus 9 plus 1, which is 14. So root 14 cube multiplied by 4 plus 16 plus 1, which is 21. So this will become 4 plus, sorry, we had to find for B. So the denominator for B was 4 plus 16 plus 1. So it was 21 only, right? And in the bracket it was, so minus 1 multiplied by 2, which is minus 2, minus 2 multiplied by minus 3, which is 6, and 4 multiplied by minus 1, which is minus 4. So this is coming out as 0. So option A is correct. Now option B says that no work is done in moving a test charge Q1 from B to C. So for this we need to find out the potentials. So the potential at B can be given as KQ by root 21. We found out R to be 21, and potential at C is also KQ by root 21. So since the potentials are same, work done will be 0. So B is also correct. And C says that 2 of magnitude of EA is equal to 3 of magnitude of EB. So let us check. 2 of magnitude of EA, which was KQ by 14 square, is equal to 3 of magnitude of, so let us check if this is true. 2 by 14 KQ is equal to 3 by 21 KQ. Both will give denominator as 7. So this is also correct. Option D says that EB is equal to minus EC. No, this is wrong because we found out that EB is equal to EC. So D is wrong. So the correct answer for question 33 is ABC. Moving on to question 34, we have a uniform spherical charge distribution of radius r produces electric fields E1 and E2 at 2 points at distance r1 and r2 respectively from the center of the distribution. Out of the following possible expressions for E1 by E2 is /r. Okay, so there will be many cases for this. So first let us define the field for a uniform spherical charge distribution. So this is given as kq by kqx divided by r cube when x is less than r, and kq by r square, sorry, I should take small r, when r is greater than r, right? I should take r also here instead of x, so that distance is represented by r in both the terms. So let us check different cases. So when both points are outside, so E1 by E2 will be given as kq by r1 square multiplied by kq by r2 square. So this will be r2 by r1 whole square. So let us check. No, this is wrong. So this does not match with any option. So let us take the second case. When both points are inside, so we will use the inside formula, which is this one, when x is less than r. So this will be kq r1 by r cube multiplied by kq r2 by r cube. So this will be r1 by r2, which does not match with any option. Since a is r2 by r1, this is not r1 by r2, so doesn't match. Doesn't match. Third is when r1 is inside, r2 is outside. So this will be the inside formula for r1, which is this, and outside formula for r2, which is this. So this will be r1 r2 square by r cube. So r1 r2 square by r cube, D option is correct. And fourth case will be when r2 is inside, r1 is outside. So E1 by E2 will be, we will use the outside formula for E1, which is kq by r1 square, and inside formula for E2, which is kq r1 by r cube. So this will be r cube by r1 square, sorry, this was r2, r cube by r1 square r2. So this is option C. So C and D is the correct option for question 34. Question 35 says two identical charge spheres suspended from a common point by two light strings of length L are initially at a distance d less than L apart due to their mutual repulsion. The charges begin to leak from both the spheres at a constant rate. As a result, the spheres approach each other with velocity v. If x denotes the distance between the sphere, then v varies as, and we have to relate v with x. So this is a question from Irodov, and this is a bit difficult, so let us start. Let me draw the diagram. Initially they are at a distance d. So let me draw at any particular instance when the distance is x between the spheres. This is L, and let me assume that this is theta. The charges are q on both. I am assuming it to be q. So, and t is here. So let me write the equations. It will be t sine theta is equal to kq square by x square, and mg is acting downwards. So t cos theta is equal to mg. So this will give us that tan theta is equal to kq square by x square divided by mg. So we also know that this distance is x by 2, and if theta is small, then tan theta can be approximated to x by 2l, right? This can be approximated to x by 2l, because here tan theta can be given as x by 2 divided by l square minus x square by 4, and since x by 2 is very small compared to the length, this is given, so this can be approximated to x by 2l. Okay, hope this is clear. So now q can be given as by cross multiplying we will get q, which is equal to okay. So now in the question we are given that the charges begin to leak at constant rate, right? So the rate of leaking of charge is constant. We will use this fact. So from here x can be given as 2klq square by mg whole raised to power 1 by 3. So this will give us velocity is equal to 2kl by mg. This is constant, and q raised to power 2 by 3. So 2 by 3 q, 2 by 3 minus 1 is minus 1 by 3 dq by dt. So this is also constant, right? So from here we will get v is proportional to q raised to power minus 1 by 3, and we know that we have to relate x and v now. So since q square is proportional to x cube, this means that q is proportional to x raised to power 3 by 2, which means that q is proportional to q raised to power minus 1 by 3 is proportional to x 3 by 2 multiplied by minus 1 by 3, which implies that q raised to power minus 1 by 3 is proportional to x raised to power minus 1 by 2. So from here we will get that v is proportional to x raised to power minus 1 by 2. So the correct answer for this question is B, C. Question 36 says that a cylinder on whose surface there is a vertical electric field of varying magnitude as shown. The electric field is uniform on the top surface as well as on the bottom surface. Therefore, this cylinder encloses. So we need to find the flux basically, because flux has two formulae, e raised to e dot product of a and also q in divided by epsilon naught. So from here, sorry, this is delta E. So we will get 800 minus 400 multiplied by A, because we are taking minus because here the A will be in this direction and here it will be in this direction, right? So 800A minus of A 400A, because the dot product will give minus here. So this will become Q in by epsilon naught, which means 400 multiplied by A. A is the surface area of this, multiplied by epsilon naught is equal to Q in. So from here we will get that the net charge is positive inside the cylinder. Question 37 says an acidic water from certain reservoir kept at a potential V falls in the form of small droplets, each of radius r, through a hole into a hollow conducting sphere of radius a. The sphere is insulated and is initially at zero potential. If the drops continue to fall until the sphere is half full, the potential acquired by the sphere is. Okay. So assume that this is acidic water. And drops are falling into a sphere of radius a. Sorry, this was a sphere. I have made it a hemisphere. Assume there is a small hole and the radius is a. So let us assume that the reservoir is kept at a potential V, right? So the potential of the reservoir is kept at V. So we can find out the charge in this drops, because the potential of this drop will also be equal to V, because it is falling from this water only and the potential here is V. So this will imply that 1 by 4 pi epsilon naught multiplied by Q by R, where this is radius of drop, this is equal to V. So from here we will get that V is equal to, sorry, Q is equal to V multiplied by 4 pi epsilon naught R. And we will also find out that assume that the number of drops, to fill the sphere half full is n. So we can equate volume n into 4 by 3 pi r cube is equal to 2 by 3 pi a cube. This is the volume of half sphere. So this will give us a relation between a and r, that n is equal to a cube by 2r cube. Okay. So now the new potential will be, the total charge is nq, right? And the radius is a. So the new potential will be equal to Q we found out as V multiplied by 4 pi epsilon naught R divided by A. So this will get cancelled out and we will be left with NVRA, and N is a variable that we assume, so we need to eliminate it. So this will become VRA cube divided by A multiplied by 2R cube. So 1R and A will get cancelled. So this will give us that V dash is equal to A square by 2R square times of V. So the answer will be option A. This was a nice question. So let us move on to question 38. Question 38 says that a hollow conducting sphere of radius 15 cm has a uniform surface charge density plus 3.2 mu coulomb per meter square. When a point charge Q is placed at the center of the sphere, the electric field at 25 cm from the center just reverses its direction, keeping the magnitude same. So therefore Q is okay. So this is the sphere of radius 15 cm and it has surface charge density 3.2 mu coulomb per meter square. So electric field at distance 25 cm will be K multiplied by sigma 4 pi r square. This will be the total charge as the surface density charge is distributed over the sphere by r square, and E2 becomes, after placing the Q, E2 will be K of Q plus sigma 4 pi r square divided by r square, small r square. So this will imply that since E1 is in this direction and E2 I have assumed in this direction, so two K lambda 4 pi r square by r square plus of KQ by r square, this should be equal to 0. So this will imply that so Q will be equal to minus 2 multiplied by 3.2 into 10 raised to power minus 6 multiplied by 4 multiplied by 3.14 multiplied by 15 by 100 whole square. So this gives us minus 1.81 microcoulomb. So answer is option D. Moving on to question 39, we have an electron and proton are situated on a straight line as shown below. The directions of the electric field at the point 1, 2 and 3 are shown as. Okay, so proton is here and electron is here. So since point 1 is closer to the proton, so we know that the electric field is inversely proportional to square of distance. So proton will have a field in this direction and this will be greater than the attractive force of E because the distance between 1 and P is less than distance between E and 1. So it will be in this direction. So A and D are wrong. And we can check on the third point because it is different in B and C. So the attracted force will be greater because this distance is lesser than this distance. So it will be in this direction. So B is correct. Question 40 says that 2 point charges plus 1 microcoulomb and minus 1 microcoulombs are placed at points 0, minus 0.1 meter and 0, plus 0.1 meter respectively in the xy plane. Then choose the correct statements from the following. So let me draw. one charge is placed here and one is placed here. So the electric field at all points on the y-axis has the same direction. So let us check. Here it will be in this direction, right? And here it will be in this direction. So A is definitely wrong because the direction is changing here and here. The dipole moment is 0.2 mu c meter along x-axis. So dipole moment will be around along this direction, right? Because it is from the minus q direction to plus q direction. And sorry, this was minus q and this was plus q. So reverse the directions also. So dipole moment is in the minus y direction. It is not in the x direction. So B is also wrong. So C says no work has to be done in bringing a test charge from infinity to the origin. At infinity, V is 0. And origin also it will be 0 because this distance is equal to this distance. So since the points are equipotential, so no work will be done. So C is correct. D says electric field at all points on the x-axis along y-axis. Let us check. So due to this, it will be here, and due to this, it will be here. So along the x-axis is along y-axis. Sorry, this due to the plus charge, it will be in this direction. So the x components will get cancelled. So the field will be in plus that direction only, and here also we can check that it will be in this direction and this direction. So the x components will get cancelled and it will be in this direction. So D is also correct. Question 41 says that two charges minus q and minus q are placed at 0, D and 0, minus d. A charge plus q is free to move along x-axis and it will oscillate with force proportional to. So this came in JEE Advanced also many years ago, and this has been repeated in 2019 in NSEP. So let me draw the situation. It is similar to the previous question, but here both the charges are negative. So assume that plus q is somewhere here. So the field here and here will be equal to, if this is x and this is d, so this will be kq square by d square plus x square, and this will also be equal to this. And if we take the cos theta, then 2kq square by d square plus x square cos theta, this will be the restoring force. So restoring force is this, and it is in the minus I direction. So I will take minus sign because it is also restoring force. So minus 2kq square d square plus x square, and cos theta will be equal to x divided by root of d square plus x square. So the force will be proportional to x by d square plus x square root raised to power 3 by 3. So this will be equal to option C. So answer of 41 is C. So 42 question says that in an inkjet printer, an ink droplet of mass m is given by a negative charge q by a computer controlled charging unit. The charged droplet then enters the region between two deflecting parallel plates of length L separated by a distance d with a speed v. All over this region, there exists a uniform downward field E. Neglecting the gravitational force, then the maximum charge that can be given to this droplet so that it does not hit any of the plates is. Okay, so let me draw the free body diagram of Q. So Q will have upwards force because Q is negatively charged, so it will have this force upwards, and it is moving with velocity in this direction. So acceleration in the y direction will be given as QE divided by m. So now the time to for the maximum charge, the time should be minimum so that it just hits here, so that it does not hit the plate and it also crosses the plate. But just after crossing, it is at the level of the upper plate. Okay, so the time should be equal to L by V. So delta y should be less than d by 2, right? So half at square, which is the displacement in y direction, should be less than d by 2, which will give us that half QE m t square should be less than d by 2. So this gives us that Q should be less than equal to mv square d divided by EL square. I've used the time from here. So this will give us the answer as option B. Question 43 says that an electric dipole placed in a non-uniform electric field may experience. So an electric field is placed in non-uniform electric field and we have to comment on force and torque. So let us check option by option. So let us first check option A. So it says that no net force and no torque. So let us check. When the field is uniform, then no net force and no torque is possible when the dipole is aligned parallel to the electric field. So something similar will be happening here. Let's see. Assume that this is the dipole and it is placed in the direction of I cap. And assume that the field is non-uniform and it is varying with y coordinate as y square plus 1. I have taken a random non-uniform electric field. So here the field will be 1 because y is 0. So this becomes a case of a dipole placed parallel to a uniform electric field, although the field is non-uniform, but is non-uniform in y direction, but the y coordinate of the dipole is same. So there will be force here minus q multiplied by 1 and here q multiplied by 1. So force is 0 and torque will also be 0 because r cross minus q is 0 because the theta is 0 degree and sine 0 is 0. Similarly, r multiplied by q will also be 0. So this implies that the torque will be equal to 0. Now let us check option B. Option B says a net force but no torque. So this is also possible. Let us see. Assume that this is the dipole. It is placed in the I direction. I cap. This is I cap. And field this time is varying with x coordinate as, let's say, x square plus 1. So assume that this is at a comma 0 and this is at b comma 0. So here the field will be, force will be in this direction, which is a square plus 1 multiplied by minus q, and here it will be in this direction, q multiplied by b square plus 1. So net force is equal to q b square plus 1 minus a square minus 1. So this is not equal to 0, and torque will be equal to, if I am taking the torque about the center point, then it will be equal to, so the center will be, let's say it is at some distance c comma 0. So the torque will be equal to 0 because torque is given as r multiplied by force. So this will be equal to a minus c cross product with minus q a square plus 1, and this is in minus I direction and this is in minus I direction. So this will be equal to 0 because I cross I is 0. Similarly, the torque due to this force will also be equal to 0. B minus c I cap cross q b square plus 1 I cap. So this is also equal to 0. So torque is 0. So option B is also correct. Option C, let us check. No net force but a torque. So we have to check when the dipole will have no net force but it will have a torque. So let us take the dipole this way. And the field is varying as x coordinate. So let us take it as x square plus 1 only, as we took in B. So the x coordinate of minus q and q is same. So force will be x square plus 1 multiplied by minus q, and here it will be x square plus 1 multiplied by q. So net force is 0, but torque won't be equal to 0 because if you take about the center point, then there will be torque because both of them are in same direction. So torque will get added up. So C is also correct. Let us check D, a net force and a torque. So this is the most obvious case. So let me take in this direction, and here field is a function of x and y both. So let us assume x square plus x square plus y plus 1 square. So let us assume that this is at a distance d and this is also distance d, and this is a distance of c. So the force on minus q will be minus q multiplied by c square plus d plus 1 whole square, and on q it will be q multiplied by c square plus minus d plus 1 whole square. So you can see that the net force is not equal to 0 because it won't get added up to 0, and also torque will be non-zero because if we take about center point, then both the torques will be in same direction and both torques are different here, unlike in question option C. So option D is also correct. So correct answer of 43 is A, B, C, D. Now let us move on to question 44. Question 44 says a point charge Q is kept at each corner of a cube of length L. The resultant force of repulsion on any one of the charges due to all the others is expressed as. Okay, so let me draw here only. There are charges here, 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 here. So let us analyze the force on any one. So I am analyzing on this charge. So I will take it as the origin. And this is the x-axis. This is the y-axis. And this is the z-axis. So let us now write the coordinates of each charge. So these are the coordinates of all the 8 charges. Now let us write the force due to each charge on this charge, which we took as origin. So it will become kq square by L cube multiplied by this vector. This is due to this charge. Now due to this charge it will be and due to this charge it would be this. I am writing the short form of vector. So this is minus L I cap plus minus L j cap plus 0 z cap. This is easier to write in this way. So I have written due to this and this charge. I will now write for the bottom charges. So it will become due to this charge it would be and due to this charge it would be and due to this charge it would be okay. So now let me combine all these terms and take out the common term. So it will be kq square by L square, and in bracket the vector will become, so minus 1 from here, minus 1 from here, and minus 1 by 2 root 2 from here, and minus 1 by 2 root 2, no sorry, minus 1 by 3 root 3 here. Sorry, here it was also 2 root 2. Now looking at j cap, it will be minus 1 from here, minus 1 by 2 root 2 from here, minus 1 by 2 root 2 from here, and minus 1 by 3 root 3 from here. Now for z cap it would be 1 from here and plus 1 by 2 root 2 from here plus 1 by 2 root 2 from here, and plus 1 by 3 root 3 from here. So these terms are also common, so I can write it as right. So now the question is asking for, it is not asking in terms of ijk, it is asking for magnitude, right? So I need to take the magnitude, so this will become I am taking the LCM here. So and the modulus of ijk is root 3. So cancelling out the root 3, we will get approximately this becomes equal to 0.8226 q square by pi epsilon naught L square, which is approximately equal to 1 minus of 0.1775 q square by pi epsilon naught L square. So this is option C. So C is correct. Now question 45 says a thin semicircular metal ring of radius r has a positive charge q distributed uniformly over its curved length. The resultant electric field E at the center O is. Okay, so let us solve this question. This is a simple question. So if this is the angle phi from I cap direction and this is the d phi, so the field due to this will be in this direction. And similarly, if we take a angle phi from here and take this element, so field will be in this direction. So the I cap components of both will get cancelled and field will only be in minus j direction. So this is theta phi also. So let me write the field due to this element in this direction. It will be equal to dE in minus j direction is equal to k multiplied by the charge on this is r d phi, and the charge distributed is q over a length of pi r, because this is semicircles. So circumference of semicircle is pi r. So q by pi r multiplied by sine phi divided by r square. So E will be the summation of these dE in minus j direction from 0 to pi. So it will be equal to so taking out the common terms we have, and the integration of this is minus cos. So I am writing cos phi and I am changing the limits. So this will give us 2k q by pi r square, which will further give us q by 2 pi square epsilon naught r square in the minus j direction. So the answer is option A. Moving on to question 46, it says a charge plus q is placed at each of the points x is equal to x naught, 3x naught. So difference of 2 between them, and so basically they are kept at odd multiples of x naught, and negative charges are kept on even multiples of 2x naught, so 2x naught, 4x naught, 6x naught. So x naught is positive constant, so the electric potential at a point due to a charge q at a distance r is given by this you already know. The electric potential at the origin due to the above system is, okay, so let me draw the diagram. The diagram is like this, and plus charge is kept at x naught, then at a distance x naught it is minus, so because from origin at 2x naught distance minus charge was kept, so from plus charge it will be x naught, and after x naught positive charge, after x naught negative charge, right? So and so on. So let me write the potentials. It will be kq by x naught minus of kq by 2x naught plus of kq by 3x naught, and so on. So it will be equal to kq by x naught multiplied by 1 minus half plus 1 by 3 minus 1 by 4, and so on. And this question came in JEE also, and it has been repeated in NSEP. So the trick is here to remember the Taylor series of ln 1 plus x. It is given as x minus x square by 2 plus x cube by 3 minus x4 by 4, and so on. So if we put x as 1 here, so we'll get this only, right? So ln 2 is equal to 1 minus half plus 1 by 3 minus 1 by 4. So the potential will be equal to kq by x naught multiplied by ln 2. So the answer is option B. Question 47 says a charged oil of density 880 kg per meter cube is held stationary between two parallel horizontal metal plates 6 meter apart when a potential difference of 103 volt is applied between the plates. When the field is switched off, the drop falls. At a certain time, the drop is seen to fall a distance of 2 millimeter in 35.7 seconds, and next 1.2 millimeter in 21.4 seconds. So the viscosity of air and density of air is given, and they are asking for various things. So let us see. I am first drawing the case when the electric field is switched off. So these are the plates, and the upper plate is at a higher potential. It is given the upper plate is at higher potential, so positive charge on the upper plate, negative charge on the lower plate, and when the drop is falling, it will eventually reach terminal velocity, and there will be mg acting downwards. Since the electric field is switched off now, there will be a viscous force above and a buoyant force above. So let me write the equilibrium equation, because when the drop attains terminal velocity, that means that the drop is in equilibrium because acceleration is 0 and velocity is constant. So it will be viscous force plus buoyant force is equal to mg. So 6 pi neta rv plus 4 by 3 density of air multiplied by pi r cube g is equal to 4 by 3 pi r cube, the density of the drop multiplied by g. So solving this, we will get 6 pi neta rv is equal to 4 by 3 pi r cube g, rho of drop minus rho of air. So here this is 880 and this is around, it is given as 1.29. So since 880 is very bigger compared to 1.29, so we can ignore the buoyant force due to air. So we will simply get 6 pi neta rv is equal to 4 by 3 pi r cube g multiplied by rho of drop. So this will give us velocity as 2 by 9 rho g r square divided by neta. Here the rho is of drop, and let us calculate the terminal velocity using this information. So the certain time the drop is seen to fall a distance of 2 millimeter in 35.7 seconds. So it will give us the velocity as 5.6 multiplied by 10 raised to power minus 6 meter per second, and from the second information 1.2 millimeter in this much second. This will come out as 5.6 multiplied by 10 raised to power minus 5 meter per second. So something like this would be happening, that when the electric field is switched off, the drop will start falling from rest. So the velocity will start increasing from 0, and it will first become this much at some time interval. Then finally the terminal velocity will be this, because you can see that V2 is 10 times of V1. So V2 is very big compared to V1. So V2 is terminal velocity, because eventually it will attain some velocity and remain there because it will achieve equilibrium. So we will take 5.6 multiplied by 10 raised to power minus 5 as terminal velocity. So this will give us R as 5.6 multiplied by 10 raised to power minus 5 multiplied by 9 multiplied by 1.8 multiplied by 10 raised to power minus 5 divided by 2 multiplied by 9.8 multiplied by 880. So radius comes out approximately as 7.25 multiplied by 10 raised to power minus 7 meters. So option A is correct. Now let us draw the situation when electric field is on. So the forces will be acting like this. Buoyant force will be acting upwards, and the electric force will be acting upwards. I am taking Q as negative. because we know that buoyant force is very small, so QE should be in upward direction for to balance mg, and since the field is in this direction, so Q must be negative, so that the force due to electrostatic field is in upward direction. And since E is constant between plates, this we already know from electrostatics, so this relationship can be used, which will give us E as delta V by d, which is 103 by 6 multiplied by 10 raised to power minus 3. So from here we will get that I'm taking this as 0. So QE is equal to mg, which will give us m, this mg, m we are not given, we are given the density, so I will write it in terms of density. 4 by 3 pi r cube, density of drop, multiplied by g divided by electric field. So this will become 880 multiplied by 4 by 3 multiplied by 22 by 7 multiplied by 7.25 10 raised to power minus 7 cube multiplied by 9.8 divided by 6 multiplied by 10 raised to power minus 3 divided by 103. So this gives us 8 into 10 raised to power minus 19 coulomb. But there will be a negative sign also, because he had assumed the Q to be negative, so that the field is in upward direction. So this is a trick question. Many people will mark this correct, but B is wrong because there is no negative sign there. The terminal velocity of oil drop under its free fall is this much. Yes, V2 will be terminal velocity because it will increase from V1 to V2, and finally it will stop at this because no more information is given. So C is correct. D says the oil drop carries 5 excess electrons. So if n is the number of electrons and Q is charge on electrons, this should be equal to the total charge, which is this much. So to get n, we can do this. From here we will get that the oil drop has 5 electrons, so option D is also correct. So 47 was actually a 6 marker question, and the answers are A, C, D. So moving on to question 48, we have 2-point charges plus Q. Each are located at 0, 0 and L, 0 at a distance L apart on the x-axis. The electric field E in the region 0 to L is represented by. So the situation is something like this. 1 plus Q is here and 1 plus Q is here. So if we analyze just to the right of this plus Q, then the distance will be very small. So denominator will be very small, tending to 0. So the field will be in this direction, in positive direction, and infinite. So it will start something like this. And if we analyze just to the left of this Q, then it will be in this direction and it will be infinite. So in negative direction and infinite magnitude. So something like this. And somewhere here there will be no field, because this direction and this direction the fields will cancel. So it will be like this. So the answer is option D. C is not correct because this has finite magnitude, and this is not correct because it should be negative here. This is not correct because the field varies as 1 by r square, which is not the equation of straight line, so B cannot be the answer. Moving on to question 49, it says a hollow non-conducting cone of base radius r 50 centimeter and semi-vertical angle of 15 degree has been uniformly charged on its curved surface up to 3/4 of its slant length from the base with surface charge density of 2.5 microcoulombs per meter square. So the field produced at the location of vertex of cone is. So this is a bit difficult question. Let us see. So the cone I have assumed to be horizontal, and this is the vertex, and theta is given as semi-vertical angle is 15 degrees. So 15 degrees, and this has a surface charge density sigma, which is equal to 2.5 multiplied by 10 raised to the power minus 6 coulomb per meter square. And so let us see the contribution of individual ring at the vertex. So assume that this is at a distance of x from the vertex. So this distance will be dx, but you can see that this thing is not in horizontal direction, right? So let me draw this here. So this distance is dx, and we know that since this angle and this angle will form alternate interior angles, so this will be theta, right? So this distance we can calculate as, this will be perpendicular, so cos theta is equal to dx by dl. So dl we will get as dx sec theta. This was the tricky part, that we do not have to take this as dx because this is not horizontal. So now due to ring, we know that at a distance x the field is given as kq multiplied by x divided by r square plus x square raised to power 3 by 2. So dE due to elemental ring is given as k multiplied by charge, which is, this was charge, right? So charge is given as the charge on this elemental ring, which will be surface charge density multiplied by the surface area of this, and surface area can be written as 2 pi x, and the radius will be, so the radius will be this, and this is x, right? So this can be given as radius by x is tan 15, so r is x tan 15, right? So x tan 15 multiplied by dx by cos theta multiplied by x divided by x square tan square 15 plus x square raised to power 3 by 2. This we have written because this ring can be cut from here and it can be formed into a rectangle, and the rectangle will be like this. This length will be 2 pi r, which is 2 pi x tan theta because r was x tan 15 and this will be dl, which is equal to dx by cos theta. So from here we can simplify this integral. We can simplify dE. So dE of ring will be equal to and tan square plus 1 can be written as sec square. So this will become x square sec square tan 15, and multiplying by 3, raising to the power 3 by 2, we will get x cube sec cube 15 degrees. And now we can integrate this to find the field, total electrostatic field. So this will become, taking out the constants, we will finally get this. And since the charge is only up to 3/4 of its slant length, so charge is only up to here, and this is the whole slant length, and this is 3/4 of slant length. So this will be 1/4 of slant length. So if we take the, we need to find this, right? So this will be equal to L/4 cos 15, and this will be equal to L cos 15. So we can put the limits as from L/4 cos 15 to L cos 15. So this will become equal to 2 pi k sigma sine 15 cos 15 log x from L/4 cos 15 to L cos 15. So finally we will get 2 pi k sigma sine 15 cos 15 log of L cos 15 minus of natural log of L/4 cos 15. So I am using the property dash ln a minus ln b is equal to ln a by b. So in denominator we will get this. So simplify this. So 2 sine 15 cos 15 can be written as sine 30 pi k sigma log of 4. So 2 multiplied by sine 30 degrees multiplied by pi k sigma ln 2. I have used this property, so this will become 2 and sine 30 will cancel because sine 30 is half, so pi k sigma ln 2, and so expanding k we will get sigma ln 2 by 4 epsilon naught. So answer is option B. Moving on to question 50, we have statement based question. So statement 1 is work done in bringing a charge q from infinity to center of a uniformly charged non-conducting solid sphere of radius r is 0. So the potential at infinity is 0, but potential at center is given as 3/2 potential is given as this, right? So since the potential at infinity is not equal to potential at center, so some work will be done and work will not be equal to 0, so statement 1 is false. This potential at center I have written due to this formula that we know that V of a solid non-conducting solid sphere is given as when the R is 0, that means at center the potential becomes equal to C by 2 KQ by R, and when R is equal to R, that means at surface the potential becomes equal to KQ by R. So let us see the second statement. The second statement says that the difference between center and surface of uniformly charged is this much. So let us find. So at center we derived that it is 3 by 2 KQ by R, and at surface it is KQ by R, so it will give us KQ by 2R. So statement 1 says that only, so statement 2 is correct, statement 2. So the answer will become option D, statement 1 false, statement 2 correct. So question 51 says that a sphere of radius r is charged with volume charge density rho such that rho is proportional to r, where r is distance from center. So variation of field with r is best represented by. So I will be using Gauss law. This is a very standard question which you will find in many books like Physics Galaxy. It is solved example. So E multiplied by 4 pi r square is equal to, I am taking when r is less than the radius of sphere. So when r is less than the radius, so it will give us q in will be equal to integral of 4 pi r square dr multiplied by the surface charge density, volume charge density, so divided by epsilon naught. This I have written because if we consider a shell at distance of r, so the volume of this can be given as 4 pi r square dr, right? 4 pi r square is the surface area of this inner shell and dr is the thickness, so it approximately comes out at this only. This is an intuitive way to find out the volume. So E multiplied by 4 pi r square is equal to 1 by epsilon naught and we know that surface volume charge density was proportional to r, so sigma can be written as rho can be written as, since rho is proportional to r, so rho can be written as some constant multiplied by r, so we will get that E multiplied by 4 pi r square is equal to 4 pi r square dr multiplied by kr by epsilon naught. So this will become 4 pi k by epsilon naught r4 by 4. So the field will finally become equal to 4 pi will get cancelled and r square will get cancelled and it will become 2. So k r square by epsilon naught 4. So this means that E is proportional to r square, right? And when r is greater than radius of the sphere, then the field can be written as this. Q in will become constant because the charge inside the sphere is constant. Since we have moved outside the sphere, so that we don't need to analyze the charge at inside the sphere at some radius, and so the entire charge is constant. So this means that E is proportional to 1 by r square, right? So first till r it is proportional to r square, so option A is wrong. Option E is also wrong because this is proportional to r, it is a straight line. Option this is also wrong because r square will have a upward concave type of graph like this, so this is wrong. D is correct because this is r square and this is 1 by r square proportional, so D is correct. So moving on to question 52, it says that 3-point charges plus q minus 2q and q are placed on x-axis at x is equal to minus d, x is equal to 0 and x is equal to plus d respectively. The value of field at a point P on x-axis at x is equal to r is very greater than d is given by this equation where there is a and n, and we have to find the values of a and n. Okay, so let us see. So the situation is something like this. Minus 2q is at center, q is at this d comma 0, and minus q is at minus d comma 0, sorry, plus q only at minus d comma 0. And they are asking for electric field at a point P on x-axis at x is equal to r greater than. So let us take this as the point. So the field here can be written as so this distance will be r minus t. So due to this the distance will be r. So and due to this it will be r plus d. Okay, so now I will take the LCM, which will give us KQ. I am taking out as common, and the LCM will be, first I am taking the LCM of this and this term, so it will become, it was r plus d whole square, sorry. So r square plus d square plus 2rd plus of r square plus d square minus 2rd divided by r minus d whole square, r plus d whole square minus 2 by r square. This I have done because these two terms will get cancelled. This is very standard while deriving many results in electrostatics chapter. So this will give us KQ 2r square plus d square, and this will become r minus d multiplied by r plus d whole square, which is r square minus d square whole square minus 2 by r square. So now I am taking the LCM of these terms. So we will get this, and now I will be simplifying the numerator. So we will get this, and this will the new denominator will be r square minus d square whole square. So this term and this term will get cancelled, and this will become, I'm taking, okay, let me solve. So 6 r square d square minus 2 d raised to power 4 by r square minus d square whole square, which will be equal to 2kq 3r square d square minus d raised to power 4 divided by r square minus d square whole square. So now we know that r is very big as compared to d. So this term can be cancelled out because this is very small, and this term can also be cancelled out because this is very small, so it can be given as since r was very big compared to d. So the terms which were in plus or minus with r and had only d, so they have been cancelled out. So this will give us 2kq 3d square by r raised to power 4. So let me now compare it with the thing that we were given in the question. So E was given as this. So Q is given as 2qd square, right? So 2qd square multiplied by 3 divided by r raised to power 4. So this will give us that A is equal to 3 and N is equal to 4. So the answer will be option C. This was a good question. And moving on to question 53, it says a static point charge Q is located just above the center C of a horizontal radius r on its geometric axis as shown in the figure. The magnitude of flux through the circle is okay. So since this delta is approaching to 0, it is given, so it will be very near to this circle, right? And so the charge which is, let me take this, and this is delta. So the charge which is below this line will all flow through this circle only, the field due to which is below this line, and above this line will not flow through the circle. So we can write it as that flux through circle is half of entire flux, right? Because this line is dividing the field in half exactly, because this delta is very small, almost 0. So half of total flux. So this will be equal to option C, which because total flux is Q by epsilon naught. So the answer for question 53 is option C. So now moving on to question 54. three small identical neutral metal balls are at vertices of an equilateral triangle. The balls are in turn touched to an isolated large charged conducting sphere whose center is on a line perpendicular to the plane of triangle and passing through its center. As a result, the first and the second balls have acquired Q1 and Q2 respectively. The charge acquired by the third ball is. So let me draw the diagram for this question. So there are three neutral metal balls which are at the vertices of equilateral triangle, and assume that the sides of the equilateral triangle are L. And a large metal ball is here and it is at a constant potential, so I am assuming the potential to be V. And okay, so when the when this thing is made to touch the large conducting ball, then the surface of both the balls should have equal potential, right? So let me write the potential on the surface of this q1 charge. So it will be kq1 by r plus kq by a, where q is the charge on this large metal ball, right? So where r is the radius of small neutral metal ball, and a is the distance between the centers of neutral ball and large conducting sphere. When they are made to touch. Because when they are made to touch, then the situation will be like this. So this is A and this is R. Okay, so the potential on the surface of this will be due to this charge Q and due to this charge capital Q. The if we take the potential due to this large conducting ball on the surface of this, we need to consider consider them as point charges located at the centers, and then we calculate the potential. So this should be equal to V. This is the first equation. The second equation will be when this charge Q2 is made to touch the ball. So it will be KQ2 by R plus KQ by A plus KQ1 by L dash, where L dash is the distance from Q1 when it is made to touch, when Q2 is made to touch the large conducting ball, because Q1 will also affect the potential because this neutral ball is now charged. So this will also be equal to V, and when this Q3 is made to touch this, then both Q1 and Q2 will affect the potential, and they are assuming that the distance from Q1 and Q2 to Q3 when it is touched the large metal ball is same. because this large metal ball is very big and these distances are very small, so we can take the distance L dash as same. So it will be, so let us now solve these equations. So we can subtract 2 from 1, so we will get, and on subtracting 3 from 2 we will get, now we can divide these two equations to get, this way we have eliminated all the variables that we had assumed like r, L dash. So this will give us, on cross multiplying, which will finally give us Q3 as Q2 square by Q1. So this is option B. Now moving on to question 55. This question came in JEE Advance also, I think 1 year before this, and this has been repeated in NSEP. So a small positively charged mass ball of mass m is suspended by a long insulated thread of negligible mass. Other positively charged small ball is moved very slowly from a large distance until it is at original position A of the first ball. As a result, the first ball rises to height h to position B such that h is very small compared to L. So choose the correct statement. So let us do charge conservation. So work done by the electrostatic force plus work done by gravity plus the work done by external force must be equal to the change in kinetic energy. And since the ball is moved very slowly, so the kinetic energy remains 0 only, because velocity can be assumed to be 0 at each point because ball is moving very slowly. So this is 0. So we will get that work done by electrostatic force plus work done by gravity, work done by external force is equal to minus of work done by gravity. Since this ball is rising height h, so work done by gravity is minus mgh and another minus from this, so this becomes mgh. Okay, now the work done by electrostatic force we need to find, and work done by external force we also need to find. So we know that the work done by electrostatic field can be given as the minus of the electrostatic energy of the system, the final electrostatic energy of the system. So work done by electrostatic force can be given as the minus of the electrostatic energy, change in electrostatic energy. Since the initial electrostatic energy is 0 because other positively charges at a large distance, since the balls are at a large distance initially, so the initial electrostatic energy is 0. I should write it as delta. So minus of mu f electro minus mu I electro, where so ui is 0, and minus of u f electro can be given as if the distance between these two balls are r, then this will be minus kq square by r, which is equal to minus of the electrostatic force multiplied by r, right? Let me draw the situation now. The situation is something like this. This distance I am assuming as r, and we were given that this is L, and this distance was given as h. This distance is also L. So now let us assume that this is theta. So since this is also L and this is also L, so this ABC triangle must be isosceles triangle. So this angle and this angle is equal. So this will come out as pi by 2 minus theta by 2, and this angle will also come out as pi by 2 minus theta by 2. Now we know that this angle and this angle is alternate interior angle, so these are equal, and this angle forms 90 degrees, so this will be pi by 2 minus theta. So this angle will be pi by 2 minus theta by 2 minus pi by 2 minus theta, which gives us theta by 2, right? And the electrostatic force is in this direction, tension is in this direction, and mg is in this direction. So now we can either break the vectors into y and x direction and then solve, or we can use another trick of force triangle. Since these three forces are in equilibrium, since this is at equilibrium, so these forces must form a triangle. So let me form that triangle. So this is ABC, right? Let me mark the things that we know. This is H. This can be written as theta, so this is L, and this is L cos theta. This is R. This is theta by 2. So and the force triangle is something like this. Vectors can be moved anywhere, so right, so I am moving mg here. Now since the corresponding sides of these two triangles are parallel, this will imply that they are similar triangles. So I can use a property of similar triangles, which will shorten our method than breaking into x and y components. We will get mg by L is equal to tension by L is equal to Fe by R. So from here we can get Fe in terms of mg by L multiplied by R, and we need to find Fe multiplied by R, right? Because then we will get the work done by electrostatic force. So this will be equal to mg by L multiplied by R square. Now R is something that we had assumed, so we need to convert in terms of L and H. So from here we can see that we can get two relationships, that sine theta by 2 is equal to H by R, and we can also get that L cos theta plus H is equal to L, because this whole length was L, right? So the components making it should add up to L. So From here we will get that L is equal to h by 1 minus cos theta. So I am writing R and H in terms of R and L in terms of H. So this will become mg. R will become h square by sine square theta by 2, and L will become h by 1 minus cos theta. This will give us mg h square. 1 minus cos theta can be written as 2 sine square theta by 2. So h and h will get cancelled. Sine square theta by 2 by get cancelled. So this will give 2 mgh. So now the work done by electrostatic field can be given as minus of Fe multiplied by R. We derived this earlier, which will be minus 2 mgh. Right. So the electrostatic energy of system is this, right? Because work done is minus 2 mgh, so electrostatic energy will be minus of that, which is 2 mgh. Total work done on the system. This is talking about the external force. So let us calculate the external force. So minus 2 mgh plus work done by external is equal to mgh. So work done by external will come out as 3 mgh. So B option is wrong, and C option is correct. Total work done on the system. This is talking about the external work. Is 3 mgh. This is correct. Work done on system to bring the two balls in their final position does not depend on magnitude of charges, right? Because 3 mgh does not contain the term q, so it does not depend on charge. So answer is ACD. We could have also done this by breaking it into x and y components. I can show you one calculation to match. So this angle was theta by 2, right? So writing the equilibrium equations in x and y, we will get, in x direction we will get t sine theta is equal to Fe cos theta by 2, and in y we will get t cos theta plus Fe sine theta by 2 is equal to mg. So I am going to be proving that t is equal to mg, which we got from here, because the denominator is same, so mg is equal to t. So let me get Fe in terms of t. Fe is equal to t sine theta by cos theta by 2. So this will give us t cos theta plus t sine theta by 2 by cos theta by 2 is equal to mg. So I will get t cos theta plus, this can be broken into 2 sine theta by 2 cos theta by 2, and cos theta by 2 will get cancelled. So I will get 2t sine square theta by 2 is equal to mg, which will give us t cos theta plus 2 sine square theta by 2 is equal to mg, and this is equal to 1 because of the formula of cos 2 theta you can derive this. So t is equal to mg. So you can get the answer with both methods, but this triangle method is a better method. So let's move on to the next question, which is question 56. So question 56 says that the figure shown 5-point charges on a straight line. Separation between successive charges 10 centimeter. For what value of q1 and q2 would the net force on each of the other charges be 0? Okay, so the net force on this thing should also be 0, right? And due to 2 mu c, this will be in this direction and this will be in this direction. So the and since this separation is equal and this separation is equal, so q1 should be equal to q2, so that the force on this is 0. So we will get that q1 is equal to q2, both in magnitude and both in sign. So now we can write on this 2 mu c. So force on 2 mu c on left side will be equal to k multiplied by q1 multiplied by 2 divided by 10 centimeter plus of k multiplied by 1 multiplied by 2 divided by 10 centimeter plus of k multiplied by, since q1 is equal to q2, I am taking both as q. Sorry, this was 20 and this will be 30. And due to the rightmost 2 mu c, it will be this should be equal to 0, right? So we will get that k multiplied by 2 multiplied by 10 into 10 q plus q by 3 multiplied by 3 is equal to minus of k multiplied by 2 1 plus 2 by 2 multiplied by 2. So this will give us, cancelling out the common terms, 10q by 9 is equal to minus 1 by 4. This is half, so half plus 1 is 3 by 2. So q will be equal to minus 9 by 10 multiplied by 1 by 4 multiplied by 3 by 2. So this will be equal to minus 27 divided by 80 mu c, since all the charges were in micro. So answer will be A. So question 57 says a very small electric dipole of dipole moment P lies along the x-axis in a non-uniform electric field given by this. So the force on the dipole is. So the force on a dipole can be given as a dipole moment multiplied by del E by del R. How do we derive this? Is we know that the potential energy is given as minus P dot E for a dipole, and force is given as minus du by dr. So this will give us, since this is constant, so minus sign will get cancelled. So we get this formula, and this formula will give us the force as P is P, and the derivative of this will be minus C by x square. So this is given by option B, so B is the correct answer for 57. Moving on to question 58, it is a bit tricky, and it says that a conducting thick spherical shell of radius A and B have been charged with uniform surface charge density minus sigma on the inner and plus sigma on the outer surface. So this has uniform density minus sigma, and this has plus sigma, right? So if we take a Gaussian surface over here, the electric field should be equal to 0 because this is inside conductor. But Gauss law will show us that in this current diagram we have electric field not equal to 0. So this means that there should be zero charge between inside this Gaussian surface. That means that there should be a plus charge here, which is equal to the negative of this charge, which is, so Q should be equal to negative of negative sigma into 4 pi, the radius is a square, right? This much charge should be located at the center, so that due to Gauss law, Qn will become 0, which will imply that electric field is equal to 0. So the question is not explicitly mentioning that there is a Q charge, but we have to assume, because only then this minus sigma is possible. This minus sigma cannot exist on its own. This will only exist when there is a plus Q in the center, right? So this will finally give us that the radial electric field outside the shell, since this is 0 total and only plus sigma, so for this Gaussian surface in green, Qn will become equal to sigma multiplied by 4 pi b square. So electric field will be given as, sorry, we know that EDA is equal to Qn by epsilon naught. So this implies that E multiplied by 4 by the dA will be 4 pi r square is equal to sigma 4 pi b square by epsilon naught. 4 pi will get cancelled, so this will give us electric field is equal to this much. So option B is correct. And net charge on the spherical shell is 0. No, net charge is this much. So option A is wrong. Radial electric field this much, no, we derived this as this much, so C is wrong. There is a net electric charge in the cavity. No, in the cavity it will be equal to in the cavity it will vary as the, if we take a Gaussian surface here, then we can calculate the electric field here, so it will not be equal to this, so D is also wrong. So question 59 says that a spherical conductor is charged up to a potential of 450 volt. The potential outside at a distance 15 centimeter from the surface is 300 volt then. Okay, so let me solve this question. So conducting shell has potential of 450 volt. This implies that kq by r is 450, right? And at a distance of 15 centimeter from surface it is 300 volts. So kq by r plus 15 multiplied by 10 raised to power minus 2 in meters, 15 centimeters, so it is 300. So if we take the inverse of both, so this will be, and this will become r by kq plus 15. So this we can put here, so this will become right. So sorry, I forgot to take the inverse on the RHS. So this will give us which gives us Q as So this will be, the LCM will be 900 and this will be 3 minus 2, so 1. So 900 by this much. So this will be equal to 15 multiplied by 10 raised to power minus 9 coulomb. So now let us find out the radius of the sphere. So kq by r was given as 450 and now we know q, so we will get r as, so this will be equal to 30 centimeter. So now let us check out the option. So potential at 15 centimeter from the center is, so since this 15 centimeter is inside the sphere, and since it is a conducting sphere, so the potential inside the sphere is constant, so it should be equal to 450 volt only, but this is 900 volt, so A is wrong. B says that charge on conductor is 1.5 nanocoulomb. No, it is 50 nanocoulomb, so B is wrong. Electric field just outside the surface is 150 Newton per coulomb. C, let us check. So kq by r square, this will be equal to this comes out equal to 1500. So no, this is wrong because there is 1 0 missing. So let us check D now. So the energy is given as kq square by 2r. This is the self energy of a conducting sphere. So this comes out equal to 3.375 mu j. So option D is correct. So moving on to question 6G, we have a small dipole is placed at the origin with its dipole moment P along the x-axis. E and V are respectively the electric field and potential at a point xy. So the observations at a point xy, which is at large distance r from the origin, show that. So let me write the known results we know from studying the chapter. So if this is theta and this is r, so in this direction the field is given as 2 kp cos theta by r cube, and in this direction it is given as kp sin theta by r cube, right? So in x direction it can be given as, this is x direction, right? So in x direction it can be given as 2 kp cos square theta by r cube minus kp sin square theta by, because this is 90 minus theta and this is theta again because this is 90 degrees. So in x direction it will be 2 kp. Okay, so cos theta can be written as x by r, right? Because this direction is x and this is r. So cos theta can be given as x by r, so x square by r5 minus of kp. Sin theta can be given as y by r. So y square by r5. So this will give us right? So option B is wrong because there 2 is here. So B is wrong and A is correct. Now in y direction we can calculate it. Y direction it will be 2 kp cos theta sin theta r cube plus of kp cos theta sin theta by r cube. This will be equal to 3 kp cos theta sin theta by r cube, and substituting cos theta and sin theta from here, it will be right, and this is what is given in option C. Now potential, we already know the formula. This is correct, so D is also correct. So moving on to question 61, it says that two equal positive charge plus q each lie on y-axis at 0, a and 0, minus a. The field at point x, 0 satisfies. So let me draw. One q is at 0, a and another q is at 0, minus a. So at x, 0, the field due to this will be in this direction, and due to this it will be in this direction. So the y components will get cancelled, and finally the field will be in this direction, which is, if this is E and this is E and this is theta, so this is also theta and this will also be theta. So this will be 2e cos theta, and this can be given as 2 multiplied by kq divided by, this is a and this is x, so a square plus x square whole square multiplied by cos theta, which is x by root a square plus x square. So this will be 2kq x divided by root a square plus x square raised to power 3. So this is wrong because here it should be x, and for large values of x the electric field is proportional to 1 by x squared. Let us check. So for large values of x we can ignore the a, so this will be 2kqx, and removing this a square, assuming it as 0, so this will be x raised to power whole cube, so this is, which is proportional to 1 by x cube. So B option is correct, and we need to find where is maximum. So E is given as right, so dE by dx will be given as right. First I have differentiated this, then I have taken this as constant and differentiated this, so this is what we have got, and this should be equal to 0 for maximizing E. So we will get, I am taking the LCM now, so and there was 2x also here, right? Because when we differentiate this according to chain rule, then 2x will also come, so this is 6x square divided by a square plus x square whole raised to power 5 by 2. So making the numerator 0, we will get cancelling out the common terms. We will get that a square is equal to 2x square, or x is equal to a by root 2. Right, so this is correct and this is wrong because x is not maximum at x is equal to 0. 62 says the magnitude of electric field due to a long positively charged straight wire at a perpendicular distance x from it is proportional to 1 by r, and the two electrons are orbiting such a long straight wire in circular orbits perpendicular to the wire with radius 1 Armstrong and 2 Armstrong. So the ratio of their speeds is asked. So let me draw. Assume that this is the positively charged long wire, and one radius is like this of 1 Armstrong and the other is like this. So at any electron will have a force here which is the field is proportional to 1 by r, right? So I am taking the field as some constant divided by r. So the in this direction it will be, sorry, since the charge on electric field is negative, so it will be in this direction. And here it will be mv square by r. So equating this we will find that v is independent of r and it will only depend on q and this constant. So this is same for both the electrons, right? So v1 should be equal to v2. So the ratio will be 1 by 1 since it is independent of this 1a and 2a. 63 says that a neutral hydrogen molecule has 2 protons and 2 electrons. If one of the electron is removed, we get hydrogen molecular ion H2 plus. In the ground state, the 2 protons are separated by roughly 1.5 Armstrong and electron 1 Armstrong from each proton. The potential energy of the system is asked. So since the magnitude of charge on electron and proton is same, but charge is the sign is different. So it will be like this. Protons are separated 1.5 Armstrong and this is 1 Armstrong each. Right, so the energy will be given as and to get in electron volts we will divide this U by 1 the charge of 1 electron, and since Q is also equal to this much only, so we will get right. So this will, on taking the LCM, this will become equal to right. So this will be equal to minus 2 kq. Sorry, not minus 2. This will be equal to minus 2 by 1.5 kq. So this is equal to minus 4 by 3 multiplied by 9 multiplied by 10 raised to power 9 multiplied by 1.6 raised to power minus 19. And there will be, since this was in Armstrong, so this will be 10 raised to power minus 10. So this will be equal to approximately minus 19.2 electron volt. So the answer is option B. Question 64 says a metal sphere is charged with a positive charge plus Q and is surrounded by a concentric uncharged spherical metal shell. Potential difference between surface of the sphere and the outer surface is V. If the shell is now given minus 3Q charge, then potential difference will be. So there is a sphere with plus Q charge, and then it is surrounded by a concentric sphere. Right, so before it is given minus 3Q, the charge distribution will be something like this due to Gauss law. So the potential difference now will be given as, say if this is V1 and this is V2, so V1 minus V2 is given as V, right? And when this will be given minus 3Q charge, so the potential inside will become, this is R1 and this is R2, right? And so this thing is equal to this thing and there is minus between, so this will also be equal to V1 minus V2, which is V. So the answer will be V only. This is a good question. So moving on to question 65. A positive charge Q is uniformly distributed throughout the volume of a solid sphere of radius r. The sphere has a smooth narrow tunnel through its center. Due to electrostatic attraction, a small particle of mass m and negative charge minus q, initially at rest far from the sphere, approaches it along the line of the tunnel, reaches the surface of the sphere with speed v, and continues to move through the tunnel. Its speed at the center of the sphere will be. So this is the sphere with charge q, and there is a tunnel through its center. This is the center, and this is the charge of mass m and negative charge minus q. So it is approaching the, it is initially at rest, right? So initial energy is equal to 0, and on reaching the surface, the energy will be equal to and due to energy conservation, energy at surface should be equal to initial energy, conservation of energy. So we will get that this is equal to this, and energy at center will be equal to the potential at center is given by 3 by 2 kq by r, so multiplied by minus q plus half m v dash square. So this should also be equal to 0, right? So we will get we are asked for the new speed in terms of original speed. So we know that this is equal to this. So 3 by 2 half mv square is equal to half m v dash square. So the new v is equal to right. So the answer will be option D. Moving on to question 66, it says two small positively charged spherical balls are suspended from a common point at the ceiling by non-conducting massless strings of equal length L. And the first ball has mass m1 charge q1 and second ball has m2 q2. So if the balls are subtending theta 1 theta 2 with vertical, then so if this is theta 1 this is theta 2 and this is isosceles triangle, because this is L, this is L, so this will be, I'm assuming, alpha. So this is also alpha, right? m1g is here, m2g is here, and force is here, and force is here. So this will also be equal to theta 1, right? And this will be equal to theta 2. And then we can find the equilibrium equation in the direction perpendicular to the strings, right? So in this direction it will be m2g sine theta 2, and since this is alpha, so perpendicular to this, this will be f sine alpha. Similarly, this will be f sine alpha, and this will be m1g sine theta 1. So we will get so from here we can get that m2 by m1 is equal to sine theta 1 by sine theta 2. So the answer is option B. Moving on to question 67, it says, it is a good question. A soap bubble 10 centimeter in radius with a film thickness of 10 by 3 multiplied by 10 raised to power minus 6 centimeter is charged to this potential. The bubble bursts and converts into a drop. Assume that the soap solution is a good conductor. Potential at surface of the drop is. Okay, so initially it was like this. This is thickness, which is equal to, and the radius is equal to 10 centimeter r naught, and after that it becomes a drop of some radius r, right? So the volume of this can be given as, it can be assumed as a sphere till radius r naught, and then it has a thickness, so it can be written as the surface area till radius r, and then we can multiply it by thickness. So this is a intuitive way to find the volume. So, and this volume will be so by volume conservation, since all the material which was forming the bubble has formed a drop now, so volume can be conserved because no material was wasted. So volume of bubble is equal to volume of drop. So 4 multiplied by pi multiplied by r naught square. This was r naught. That's the new radius. This is the new radius. So now we need to find the potential at the surface of the drop, which is kq by r, right? And from here we know that the initial potential of the bubble was 80 volts, which is equal to k q naught by r naught. So q naught can be given as 4 pi epsilon naught r naught v naught, sorry, v bubble. And now since all this charge was also transferred to this drop, right? Because no charge was left. So by charge conservation, q naught is equal to q of drop is equal to this much. This is potential. Don't get confused that it is volume. So I'm writing this as v naught only. So the potential of the drop will be equal to k q naught by r, which is so this will be equal to 80 multiplied by 10 raised to power 2, which is 8 kilovolt. So the answer is D. So question 68 is a very nice question. It says a charge Q is uniformly distributed throughout the volume of a non-conducting sphere of radius r. The total electrostatic energy of electric field inside the sphere is alpha multiplied by q square by 4 pi epsilon naught r. The value of alpha we have to find. So we know that the self potential of ring and sphere we already know of non-conducting. Let me derive self energy. So we know that all the charge has to assimilate on the surface of this ring, right? So if this is r and this is the dq, so the work done to bring this dq charge will be v multiplied by dq, which is k q by r multiplied by dq. Q is the charge that has already been assimilated, and dq we are bringing from infinity. So the work done to bring 1 coulomb from infinity to this radius r is v, right? That is the different definition of v. So for dq it will be v dq. So now we can integrate this. From 0 to q it will be this much. So we get this as kq square by 2r. Now I will be deriving the self energy of non-conducting sphere. So assume that we have already made a sphere of charge q and radius r, and we are bringing dq charge from infinity to here. So if total charge is q and total radius is r, capital R, so charge density can be given as the q divided by 4 by 3 pi r cube, which is 3q by 4 pi r cube. So charge q on sphere of radius r is given as rho multiplied by 4 by 3 pi r square, which is equal to 3q by 4 pi r cube multiplied by 4 by 3 pi r square. 4 pi gets cancelled, 3 gets cancelled, so this is q r cube by capital R cube, right? So now the elemental charge can be given as the derivative of this, which is right, and work external can be given as the total work is the integral of small work, which is v is kq by r and dq, and dq can be replaced, so it will become kq by r multiplied by 3 r square q r cube dr, and q is not constant here, so we need to represent in terms of r only, so that we get all the variables in terms of r. So this will become, q is not constant because this is the charge at any one point, and we are constantly bringing charge till the total charge becomes capital Q. So this will become which finally gives us from 0 to r, which gives us 3 by 5 kq square by r square, no, kq square by r. So this is the self energy of a non-conducting solid sphere, right? These two results you might already be knowing. So now let us analyze the question. So the question is asking for the electrostatic energy of electric field only inside the solid sphere. So 3 by 5 kq square is energy due to entire field of non-conducting solid sphere, right? Which includes the internal electric field plus external electric field. And we know that this kq square by 2r, which we derived for a non-conducting ring, since the field inside a ring is 0, so this is the total energy due to entire field of non-conducting ring, and since ring has only outer electric field, so since inner electric field is 0, from outside both ring and sphere will look same. So outer, so energy due to outer electric field of outer electric field of solid sphere, both will be same, right? So inner energy due to can be given as the difference of both, right? Which will be equal to 1 by 10 kq square by r. So the answer is option D, right? Another method is, if you have read the chapter capacitors, then energy density is given as half of epsilon naught E square, and E inside the uh, electric field is E inside the solid sphere is kqr by r cube. So we can find the total energy inside the solid sphere. It will be right, because the if this is equal to U, then the total energy will be given as this, right? And dq sorry, dv, right? U multiplied by dv, because this is the density, and if we multiply density with volume of elemental ring, then we will get this, and if we integrate the rings from 0 to r, then we will get the entire energy. So this also gives us 1 by 10 q square by, so 1 by 10 is the answer, right? This was a good question. I have given two methods. So moving on to question 69, we have a thin plastic disc which has quarter of a circle of radius r, 0.6 meter, lies in the first quadrant of xy plane and with the center of curvature at origin O as shown. It is uniformly charged on one side with surface charge density sigma, so electric point at this point. So we know that due to disk, it will be potential is right, and due to quarter disk will be 1 by 4 of this, because potential is a scalar quantity and it is we don't have to deal with directions, so we can have an intuition that it will be 1 by 4 times, and where x is this direction, sorry, if this is the disk and this is the point, then this is x and this is r, right? And this is theta. So it will be 1 by 4 sigma by 2 epsilon naught 1 minus 0.8 divided by 0.8 plus 0.6 whole square. 0.8 square plus 0.6 square is 1, so it will be which is 2 by 10. So it is 1 by 40 sigma by epsilon naught. So answer is option D. Moving on to question 70, it is a very common question and many people know that the answer will be uniform. So a uniformly charged non-conducting sphere with its center at C carries positive charge and uniform charge density plus rho, except in spherical cavity with center O. So the electric field inside the cavity. So let me draw a general diagram. They are asking for the field at center. I will prove that at any point the field is same and constant. So if this is C1 and the center of this is C2 and I am finding at any point P, so this can be assumed as a larger sphere of the electric field at P due to a larger sphere of charge density rho, and at P due to a smaller sphere of density minus rho, right? Because if we add minus rho sphere here, it will become this cavity. So the answer will be this I am taking as small r and this I am taking as capital R. So we get that the electric field at P is C1 P minus C2 P can be understood from here that this is C1, this is C2 and this is P. So C1 P is here, C2 P is here. Sorry, this is minus C2P, right? So minus C2P will be here. So this can be given by vector sum rule as this, which is C1 C2. And since this is also constant, this is also constant, so the electric field will be uniform. So we have completed all the 70 questions of electrostatics previous year questions of NSEP, and let me know in the comment section which chapter do you want next for NSEP solutions. And I'm also going to be continuing the series which has the best questions from various test series for physics, chemistry and maths, so look out for that also, and don't forget to like and subscribe. Bye.